Welcome everyone. Welcome to the first afternoon session of the Big Tech Day. You can hear me, you can see me, I hope. Thank you all for being here. I hope you had a nice lunch break, both on location here in Munich or wherever you are right now. We are live in YouTube, we are live in the webinar, and we are streaming to the room Partenkirchen in the Western Grand Hotel. Before we welcome our speaker in a moment, start the presentation, let me go through some quick announcements. Number one, we will record this whole session. So if you participate in any way, for example, by asking questions on site, you will be recorded as well. Please keep that one in mind. After the presentation, we're gonna have some time for questions. So please save your questions for until after. And we will only allow questions via Slack and in person from the Western Grand Hotel. So if you have any questions, please join our Slack channel, and please understand that we cannot monitor the question functionality in the Zoom webinar. Okay, perfect. And now to the part why you're all here. Now we have a presentation in the category Hardware and Reality Hacking, and it is titled A Tale of the Untold, the Physics Behind Extreme Jet Aerobatics. And it is about the art of aerobatics are typically performed by much lighter planes, sometimes planes specifically built for that purpose. But despite their enormous weight and completely different design considerations, fighter aircraft are able to perform extreme maneuvers. And with us today, we have Alejandro Ibáñez to share his enthusiasm and knowledge on the topic. Alejandro Ibáñez is an artist entrepreneur moved by an intense passion for the aeronautic world, which led him to get his bachelor in aerospace vehicle engineering. His interest is focused on fighter aircraft, extreme postal aerobatics, and aviation shows. After 18 years of designing, building, and flying model aircraft, he is now working on his next aircraft prototype, which he hopes to eventually manufacture and distribute for the RC hobby market. Alejandro also runs Air Guardian, a YouTube channel dedicated to aviation with 50,000 subscribers and more than 20 million views. Alejandro, thank you very much for being with us today. Everyone, please welcome our speaker and enjoy the presentation.
Thank you very much, Christian. It's an honor to be here today, and welcome everyone to the talk. And thank you very much for attending. So today we are going to talk about the physics behind extreme aerobatics. Christian has already introduced me, but one thing that I would like to put emphasis on is the fact that I have been able to combine my engineering knowledge with practical experimentation through model aircraft. And this has given me really valuable insight into how these fighter jets work ultimately. So here, for example, you have in the small screen a video. Oh, by the way, all the media that you will be seeing in this presentation is taken from my YouTube channel or from my personal picture collections. So it's all filmed by myself or by my father. And what you're seeing here, this is my model aircraft, a small replica of the Su-35 on the big screen. And on the small screen, you have the real jet. And as you can see, they can be made to behave very similarly. Of course, there are some differences, and you need to slow down the footage of the model aircraft so that it looks realistic. But ultimately, they are more alike to each other than most people would think. So what is the aim of what I really look forward to achieve on the talk today? So many of you may have already been to an air show, or at least you have seen fighter aircraft in movies or YouTube videos. But I think it really takes to personally getting to an air show to experience this first person, to stand next to one of these machines, to really get amazed with it. And I would love in the future, if you attend such a show, or you see maybe the Top Gun movie that is coming up, you will see what these planes are doing, and not just be visually amazed, but also get a basic understanding of what is going behind all this. And of course, let's have fun. And I want to spread the virus of passion for aviation. That's what this is all about for me. And in order to achieve this, I have divided the talk in 3 main blocks. That is an introduction or background, in which I will explain how I came to be fascinated by this topic, and a brief discussion on the tools that we were taught at university in order to understand flight. Then we will move on to fundamental concepts that I think are necessary to understand the topic at hand. And finally, the fun part, which is I've made a selection of very iconical extreme jet maneuvers, and we will be dissecting those. Then I'll make a few last remarks and move on to the Q&A. And before we move on, first of all, I need to talk about what is a STOL, because the title for the talk is Extreme Jet Aerobatics. But by extreme jet aerobatics, what I really mean is post-STOL aerobatics. That is a streamlined object moving through a fluid usually produces a very smooth flow. But as this object starts developing angle of attack, or alpha, as it's usually referred to in engineering, the flow has problems trying to keep attached to the surface of the object, and eventually it will detach. When airflow detaches from a surface, it creates all sorts of chaotic, swirly motions that, for the most part, one tries to avoid. And we will see why is that. So this is what STOL is, and why is that relevant? Well, post-STOL aerobatics, as the name indicates, happen in post-STOL regime, and most of the things that we are taught at university stop when STOL begins. So all this talk essentially is going beyond university teachings in many regards. Here you are seeing aircraft that are performing maneuvers in which the flow is practically entirely detached, but still these aircraft are able to retain control authority and keep flying. And without further ado, let's get started with the first block. And I've titled this From YouTube to Engineering, and the title may sound a little bit weird to you, but it makes perfect sense. I mean, I was already playing with toys like small airplanes. Later on, I would go to video games on fighter jet as a child. But at that time, I was not really interested so much in aviation. What really sparked my interest was when, as a teenager, I discovered videos of Russian aircraft performing seemingly impossible maneuvers on YouTube. That's where it all began for me. That's what really marked the difference from being just something that I knew about to being something that somehow I wanted to dedicate the rest of my life to it. Like, really, just look at what you are seeing here and try to wrap your mind about how such a huge aircraft is able to perform these kinds of maneuvers. Like, these jets are often in the 20 to 35 tons range. Just so you get an idea, it's like taking 3 city buses, wrapping them together with duct tape, and then imagine these duct tape buses performing backflips at 400 kilometers per hour, plunging through the skies. Like, try to wrap your mind about that. I don't know you, but for me, this is fascinating. Which leads us to university. This became such a passion, or even you might say an obsession, that I needed to know more about it. And I decided to enter an aerospace engineering degree in order to find out more. So actually, in fact, I was not able to enter an aerospace engineering degree directly because my qualifications were not high enough. So I instead started with industrial engineering. I then repeated the access tests, and then I managed high enough qualifications to be allowed in. So, hey, I'm in. Now I will get the tools to get the answers that I have been craving for, right? Well, not quite. I mean, I was expecting university to be hard, but I was also expecting university to deliver much straightforward answers. They certainly delivered me many tools, but the answers as such to the questions that I was asking myself, they did not come forward as easily. Individuals that are knowledgeable on this topic are really hard to come by. The subjects didn't touch very on these aspects in a deep way, and professors, for the most part, lacked answers. They were very knowledgeable, of course, in their respective fields, but many of the questions that I would ask them, they would just have no answers for. Here, for example, we're seeing Su-30 SM. This is a Russian airplane, and you can see highlighted in red are what are called canards. And I saw many planes use this, many didn't. And one of my questions was, well, what are these for? I mean, I more or less get an idea of what they can be doing, but why would you mount them on some aircraft and then not on some other? And I asked this to my aerodynamics teacher, and with all honesty, credit where credit's due, he just told me, I don't know, which, because he could have made anything up, and maybe I would have been okay with that. But since he did not give me an answer that kicked me on my own spiral of research to find out more about the topic, which eventually I think it led me to a deeper understanding on the subject. So this is all about modeling fluid fields as far as the university part is concerned, right? If we know to understand how an aircraft is flying through the air, we need to understand how the air behaves around the aircraft. And from being able to accurately model the behavior of fluids, we can derive properties such as velocity and pressure, which will give us clues as to why the things are happening. And there are three main tools that we are either taught or at least presented during university. The first one would be potential flow. This is what is understood as classical aerodynamics, pretty much developed in the 1920s, but still relevant today. And this is an analytical method, heavily based on mathematics. Then we have a computational fluid dynamics, very commonly known as CFD, which more or less was developed about the same time, but at least the foundations, but it only became readily available for use later on because we did not have enough computation power back in the day to make use of this tool. And finally, we have empirical research, that is to make a scale replica of what you are trying to research and test it in a wind tunnel or by other equivalent means. Now, so what is potential flow? Here, I would like to make a comparison that for many physicists and engineers is very relatable. Like we are taught that you can represent any sort of wave through superposition of simpler waves, like sine waves. This is what is called the Fourier transform. And this is extremely useful, right? Well, for potential flow, there is a very similar thing going on. And you can take simplified and elementary flows, and you can put them together and represent more complex fluid fields. But you could virtually represent pretty much any fluid field around an airfoil. But you need to start specifying conditions so that it's not just an arbitrary result, but one that approaches reality. This is what it's called the Kuta condition. And basically what you need to understand is that it forces the fluid to exit smoothly at the trailing edge of the airflow. Then all this can be extrapolated to 3D through further methods like Prandtl lifting, line theory, and others. So potential flow is fantastic for study of wings at small angles of attack, but again, we are going to be using really huge angles of attack in extreme aerobatics, so really not useful in that regard. Which brings us to the next one, which is CFD. This is a numerical method based on the Navier-Stokes equations. That is essentially Newton's second law applied in a fluid context. What you do here is you discretize space in a number of control volumes, and then you try to solve these equations that describe the behavior of fluids for each and one of those control volumes. And there are different numeric approaches to solve this. But the thing is, now Navier-Stokes equations are really, there are some of the most relevant equations from the 20th century. And essentially, it's, as I said, it's Newton's second law, like force equal mass times acceleration. And when applied in the context of a fluid field, you have this force per unit volume essentially broken down into pressure forces, forces from viscous origin, and external forces like from gravity or electromagnetism. And once you simplify these equations for the case that would apply to an aircraft, that is an aircraft flying at subsonic speeds, for example, this is incompressible flow, so density remains constant. And other simplifications, you still are left with a set of pretty heavy partial differential equations, which is what you can see now on the screen. So, and of course, you do not have an analytical solution for those, but you can make numerical approximations. That's why this is a numerical method. CFD allows us to tackle much more complex problems, so to speak, but it requires huge computing power, and which is one of the drawbacks, but it also is still difficult to tackle the problem of boundary layer separation. That is when stall happens. You need to contrast your CFD results with those of empirical research in order to really have really accurate predictions, which leads us to the last one, which would be empirical research, which would be really the best tool we still have nowadays to understand fluid motions. But it's crazy expensive. Like the installations you need for a serious wind tunnel are like huge. These are huge buildings. It's like not something you will build in your room. And then even then there are drawbacks. You need to take things into account, like you can scale down a model, but you cannot scale down air molecules. So you need to apply some correction factors so that what you're witnessing at a smaller scale will apply also to the larger one. And also model aircraft can be used in that regard. So in essence, I had a lot of questions. I entered an engineering degree, which gave me tools, but for the most part did not answer those questions. And I went to third-party sources. I researched scientific papers, literature. I went to people that I knew something on the topic, online forums. Then I was able to experiment with my own fighter jet model aircraft. And through analysis of videos, both of my jets and of the full-scale ones, I was able to learn a lot. And here I will start the second block, which is fundamental concepts. First and foremost, you need to understand what each axis is called, because I will be mentioning this quite a few times. So yaw is like the steering wheel on your car, like when you go to the left and right, this is what is called yaw on an aircraft. Then you have pitch, which would be to nose up or nose down, pitch up, pitch down. And roll would be balancing around your longitudinal axis. And here, let me get back to airfoils and fluid fields. because it's interesting to note that we are not going to talk supersonics. Supersonics are a whole different topic, and well, when a fighter aircraft is performing the maneuvers that I have been showing here, it's not flying at supersonic speeds, because pulling those maneuvers at those speeds will, the pilot would die, like and the plane will blow in pieces. It just does not happen. So we will focus on subsonic, and at subsonic speeds, you need to think of airfoils moving through air as warning air in advance. So the air knows that an airfoil is coming before the airfoil gets there. A way to think of this is that the presence of the airfoil is, this data is traveling through pressure waves, just like our voice would do at sound speed. And to understand how lift is produced, we have Bernoulli's principle, but long story short, what you need to take from here is that as long as the fluid behaves in a smooth and streamlined way, basically the fluid particles are moving along the streamlines parallel to them. So a constriction in area produces an increase in speed, and an increase in speed through Bernoulli's principle brings a decrease in pressure. So this is what dictates the distribution of pressure around an airfoil, and all the aerodynamic forces result from this. Then we need to talk about what boundary layer is, and this is a real airflow is viscous, so the area has some viscosity to it, and it is sticky. It wants to stick to things. So when you have a fluid moving through space, air is trying to attach to its surface. Or if we see it from a fixed perspective on the airflow, like you would, for example, on our wind tunnel, the airfoil is fixed and airflow is moving around. You can see as the airflow has an energy because it's the one moving, and then it loses that energy through viscosity and shear stress as it approaches the surface. And the space where this is happening and the fluid is losing speed is what is called the boundary layer. And boundary layer, once it loses enough energy, a phenomenon can happen, which is flow reversal. Like fluid likes to travel from high pressures to low pressure zones. You probably know this from weather forecast, right? Well, in an airfoil, sorts of happens the same. So as the airflow moves along the airfoil towards the trailing edge, the pressure has increased. If it has increased high enough, then the flow will reverse and start flowing along from the trailing edge to the front of the airflow, and this causes the airflow to separate. This is essentially stall, and it gets worse as the plane increases angle of attack. So here you see coefficient of lift, which is directly proportional to the lift that an aircraft generates. And once you for the first angles, this increases linearly, but then when stall happens, it drops sharply, and you start producing lift, which would be the component of airspeed that is perpendicular, the component of force that is perpendicular to airflow, the one that keeps you flying, essentially. There are many ways in which an airfoil can shape and form in order to try to improve this and delay stall. Like one typical thing that airplanes do is to allow high pressure air from the underside of the wing to the top by making gaps. And what this makes is you are infusing fluid that has high energy from the high pressure into, you accelerate it to the part of the airflow where it's starting to slow down, and then you give it a little more edge in speed and can delay stall. And a quick note, so far I have been talking about stall as a separation of fluid, but from a pilot's perspective, you need to also understand stall as a loss of control over an aircraft. The two conditions are often related, but they are not exactly the same. Like you can have an airplane that has separated flow, but has not yet reach the point where the pilot lacks complete control over it. And this leads us to how airplanes are controlled. So essentially the airfoils can often move. So on the bottom left corner, you can see a conventional control surface, that is, the airfoil is fixed and the trailing edge can deflect up and down to change the pressure field and the forces that are generated. Or immediately below, you have a full flying style, that is, the whole airfoil will pivot around an axis. And one way or the other, what you are doing is you're redirecting flow upwards or downwards. And so mass times velocity, you are changing momentum, you are changing the momentum of airflow, and by reaction, the air is also conveying momentum to the aircraft in opposite directions, so to speak. And so far we've been talking about two-dimensional effects, but now we need to get into three-dimensional effects. So now we have a fighter jet that is coming right at us, and we can see that, as we have told before, the pressure under the wings is higher than the pressure on top. And for a wing with infinite span, it would be like this forever, but real aircraft cannot have wings that stretch to infinity, and at some point the wing stops. And right there, the high pressure air will attempt to swirl around to get to the low pressure zone, and this creates a vortex. And also, as we have already seen, in a subsonic condition, what happens downstreams also affects what is coming upstream. So it's not just a local phenomenon on the tip of the wing, but this affects the whole flow around the aircraft. And right underneath, you can see the typical shape that the wake of an airplane takes. And that is, it is very easy to remember, because it's a happy face, right? It's a smiley. You have two eyes, which are the vortices, and a smile. And from this, you can easily picture what is happening to the airflow. So it's going up on the outward portions where there is no longer aircraft, and in the inside, it's going down. This is very, very relevant. Here, for example, you're sitting one of my model aircraft of our JAS 39 Gripen, and I have attached smoke cartridges to the wingtips to see these patterns being formed. And you can sort of see that happy face in there. Here we have a Chinese J-10B, which is a plane with a similar layout. And you can see the effect that not only vortices are formed, but the whole wake after the plane is going down. Stay with me, because this is really important. Wakes are, you are giving downwards momentum to the fluid in order to keep the airplane afloat. So this airplane is not climbing, it's flying at a constant altitude, but still the airflow is going down. And this is important because you can use canards, like going back to what I was explaining first, what are canards for? So on an aircraft that does not have these canards, the stall will begin sooner as you increase angle of attack. But by adding canards, this is akin to using a small wing ahead of your bigger wing. And by doing this, you are doing two things. You are deflecting the wake, so the canards are changing the effective angle of attack that the main wings see. So the main wings suddenly do not see the airflow as coming from straight ahead, but with a shallower angle. So this already helps in delaying the onset of stall. But then also canards produce vortices the same way that a wing would do. And you can use the rotation of this vortex to mix the airflow. If you see here on the bottom left corner, there's the speed profile that I showed earlier for an airfoil and how it was losing energy. But you see that the airflow that is separated from the profile, it has a lot of speed. So if you induce a circular motion here, you can bring that airflow that has a lot of speed and bring it in contact with the surface. So you are, again, putting energy where energy is bleeding off. And allow these airplanes to perform better. I explained this for canards, but the same thing can be said of leading edge root extensions or lurks, strakes, and delta configurations, like wings that have a very acute wing sweep. That is, that the wings are like spread backwards. This is a MiG-29 M2, and you can see these vortices happening like here and here and here. And this would be a diagram that may be more easy to comprehend of what is going on. But there's nothing such as a video. Here we have a Su-30 SM, and if you look carefully, you can see vortices forming. Let me stop the video right here. This is one vortice, this is another one. So this one corresponds to the leading edge root extension. This one corresponds to the wingtip of the canard. And this is changing the entire fluid field around the aircraft, particularly over the wings. And this has huge implications for how much angle of attack these aircraft are capable of withstanding. Now, I would also like to talk, now that we are getting into the thick of it, it's interesting to understand what happens when you do not have a streamlined object, but a blunt one, like you can have a cylinder or a plank, and airflow no longer behaves smoothly because airflow has a problem to keep its pace around sharp corners. So vortices will shed, the airflow will detach from the surface. And as we have seen, this can be put to good use to improve the lifting conditions and of an airfoil. But for a cylinder in particular, you can have these vortices interact with each other in a periodic fashion. And this leads to oscillations and vibrations, which is something you definitely do not want on an aircraft because it can be destabilizing. And also a plank pretty much behaves in the same way. And you are going to tell me, but a plane is not a cylinder or a plane is not a plank. Well, they may not be when they are flying straight, but once they reach 90 degrees angle of attack, this is the plane, this is the airflow, and suddenly the plane, it's behaving like the whole shape of it is more like a plank, and the cross section of the front fuselage is usually a cylinder. So again, this is relevant. And another thing that I want you to understand is that as a plane speeds up, it requires little angle of attack to produce lift. And the slower it flies, the more angle of attack it needs to produce to come the same lift. And now is where the fun part really begins, which is modeling flight dynamics. Like at university, we are often taught about the 4 basic forces of flight, that is thrust, pushing you onwards, a drag, the aerodynamic drag that is keeping you backwards, the lift that will fight the way to fly in the air. And then you break down this into even more complex systems, like you will break down lift into the lift of the tail on one end and the lift of the wing on another. You will also do this as a lift plus a torque applied to them. And this is fantastic for modeling things mathematically because you can make a bunch of simplifications. But this is not visual, so this is not what I'm going to do here. Instead, I want you to picture forces around the aircraft in a different way. I want you to see that basically, ignoring thrust, we have just 2 main forces, that is gravity forces and aerodynamic forces. Gravity forces, by definition, act on the center of mass of an airplane, so they cannot cause rotation over the body. I mean, in space, there's such thing as tidal locking, but that's way out of the scope and pretty much not applicable to atmospheric aircraft. So forget about that. Gravity forces will not cause an airplane to rotate by themselves. What makes an airplane be able to rotate is the distribution of pressure, which we can take a as a resultant force, which here I have painted as F, applied on a center of pressure, no torque. So if the center of pressure coincides with the center of mass of the aircraft, then there's no torque being exerted and the airplane will fly straight. If the center of pressure is shifting forward of the center of gravity, then the plane is going to pitch up, and conversely, if it shifts up, the plane is going to pitch down, right? Force time distance exerts a torque, and the body will rotate around its center of mass. So with this in mind, it's much easier to start to begin to understand how these aircraft performing extreme maneuvers behave the way they do. And I don't know if this picture I made here is really easy to understand, but I will try my best. So here you're looking at an aircraft with a like 45 degrees angle of attack that is coming straight at you. And you have the center of gravity, which is always at the same point. And what is happening is that this aircraft is deflecting its control surfaces. Like in this case, it would be canards on the front and tail planes on the aft. And there's many things that affect lift, but surface is one of them. And you can picture a plane when it's reaching extreme high angles of attack. When you are deflecting control surfaces, what you are essentially doing is you are changing the amount of area ahead and behind the center of mass. So by making more or less area, you are moving the center of pressure. And as we talked earlier, shifting center of pressure means we can steer the aircraft around, like making it go up, making it go down. And so far, I have thought about controlling the aircraft with conventional controls, but to understand extreme aerobatics and post-stall maneuvers, we need to talk about thrust vectoring. So even before thrust vectoring, understand that thrust is a force, so it will act on a line. And if this line intersects with the center of mass of an aircraft, essentially the plane is going to fly straight. If it does not, then it is also causing a torque that needs to be compensated. And some aircraft engineers were smart enough to see that, oh, well, actually, we could use this to our advantage, because when a plane stops flying at speed, we lack the ability to control this airplane with enough authority from conventional controls. So instead, you can move thrusts around, like you are pointing the direction of the thrust vector, hence thrust vectoring, to cause a torque that is allowing you to move the aircraft. And in the video, you saw a 230 SM that is pushing up and down on the stick, and you can see how the nozzles are moving in addition to the tail planes. This is a close-up of what nozzles like such in a Su-35S aircraft look like when inspected close-up. You can see that they can deflect quite a bit. And there are many types of nozzles. Essentially, you have one-dimensional nozzles where they will go up and down. Then you have two-dimensional nozzles where they go up, down, left, and right. So on typical two-engine aircraft configurations with 1D nozzles, that is the top right picture. This allows you to have pitch and roll control over the aircraft when you would otherwise be deprived of effective control. Then if you have 2D nozzles, you also have control over yaw. But Russians devised a very smart way to get rid of the second axis, which essentially means saving weight on the aircraft by removing actuators. And that is to tilt the axis at which one-dimensional nozzles actuate. So for example, if we break down this in forces, this would be like looking an aircraft from behind, and the orange would depict the force that is being produced by a set engine or nozzle, and this is broken down into two components, one vertical, one horizontal. The vertical is going to produce a roll moment, and the horizontal is going to produce a yawing moment. So you still get control over the three axes with help from flight computers. And I am running short of time. So here I could talk about stability and control, which is also very relevant, but I'm going to skip it because we will not have time. Let's start here the third block of the presentation, which is really what we were here for, which is to discuss extreme jet aerobatics. And the first one I want to talk about is sustained high alpha. So here you're seeing, again, a Su-30 SM. This one has the whole thing. It has canards, it has tailplanes, thrust vectorings, flaperons, rudders, and you were seeing it performing a sustained flyby at around 70 to 80 degrees angle of attack. Now, in this other video, this is me flying some of my model aircraft, replicating more or less the same moves. One thing that needs to be understood, this is a very difficult maneuver because, as we said, in these conditions, the airplane is starting to behave more like a plank and less like a streamlined object. And if you see the top right image here, you can see an airplane from above. And if it is flying, say, at 90 degrees angle of attack, like it's completely perpendicular to the airflow, it's going to shed vortices. So the fuselage is like a cylinder, the wings and the rest of the aircraft is like a plank. And these vortices may not be shed in a homogeneous fashion, but they may alternate in strength. Like if you see closely here, you can see that my aircraft is tilting to one side and the other as a result of this. There are a few more examples here that are pretty visual and make it easier to understand. So to be able to hold control of an aircraft in such conditions, you really need to try to ensure, here, 1 second, look here. Here you can see the vortices alternating between left and right, which is a problem that needs to be overcome. And you also want, there's also what is called Dutch roll, which is more from, we could say, it comes from a potential origin, but it has much the same effect, and both can add up. And so here, thrust vectoring is pretty much the key solution to have the plane in control, because control surfaces are almost deprived of authority. And another maneuver, this is pretty much the first extreme aerobatic maneuver that one thinks about, which is the Cobra maneuver, or Pugachev's Cobra. So essentially the plane is going from flying straight, then it pulls sharply to 90 degrees of angle of attack or even farther, and then the nose comes back down. And through the entirety of it, the airplane retains forward motion. The previous video was a real MiG-29. These are my model aircraft. And as you can see, you can replicate the maneuvers of the big scale aircraft with smaller models. This maneuver requires a very particular design, because you need to be able to shift the center of pressure with angle of attack, such that when the maneuver begins, it moves forward, but then as you reach extreme high angles of attack, then it shifts back so that the nose can come back down again. So not all aircraft can properly perform this maneuver. And even if they can perform the maneuver, what is really tricky is to recover from them, because, okay, you can pull on the stick and the aircraft is going to rotate, but then you are left with no speed and you still want to exit forward, and you have no control over the aircraft. So again, thrust vectoring plays a great part, but with a very good design, you are capable of making this maneuver even without thrust vectoring. Then we have Frolov's chakra, or the cool bit, and this is like taking a Cobra to the next level. So you are pulling on the stick, but then you are not going back. You are completing an entire rotation. This maneuver is really mind-blowing. Again, that was a real Su-35, and here we have 3 of my model aircraft, all performing the same maneuver. And one thing that I would like to point out about this one is that it's pretty unstable due to one thing that is called the intermediate axis theorem. You may be already familiar with this, even if you have not heard it by this name. Maybe you have tried flipping your cell phone and you have found that it's very difficult to flip your cell phone without it producing weird tumbles in the sky. Or maybe you are familiar with a viral video on the internet that spins a T-handle in space. And this rotation is not stable. It spins in one direction and then suddenly flips and keeps spinning in the other direction, then it flips again. Well, I will not go into details, but this happens because an object is spinning around its intermediate momentum of inertia. So not the moment of maximum inertia, not the moment of minimum inertia, which produce stable rotations. And it just so happens that the pitching axis on a fighter aircraft is the intermediate moment of inertia. And if you mess up this maneuver, then the plane is going to fall out of the sky in a very weird fashion. I do not have video of this now here, but maybe if you're interested, you can ask me later and I can provide something privately. Then we have flat spins. So right now we were seeing longitudinal maneuvers, and this is a lateral one. So essentially you have the aircraft is falling, it's plunging through the sky. And traditionally when an aircraft entered the flat spin, the first thing the pilot would do is eject, because most aircraft were not able to recover from flat spins. But nowadays, particularly with modern fighter aircraft, you are capable of putting the aircraft in this condition and coming out without any sort of problem. So thrust vectoring plays a part, but it can also be performed without the help of thrust vectoring. Essentially, even without thrust vectoring, just with differential stabs that are painted blue and orange in this picture, you can do this. If you take the half of the screen, you have the reactions on the stabs when a pilot produces a roll input on the aircraft. And that is one stab deflects up, the other deflects down, and this produces a torque, which is going to make you roll to the right in the case portrait here. And on the bottom half of the screen, now the plane is no longer flying aligned with airflow, but it is at 90 degrees, just as it would be more or less in a flat spin. And the exact same input, like pulling full roll to the left or to the right, will produce a yawing output in the opposite direction. So I will not get stuck here now, but you can come later and watch the replay of this and think about this, because here it may seem like difficult, but it's really not, once you take 5 minutes to think about it. And again, I do this all the time with my model aircraft, most of the times, even without using thrust vectoring. And it's a beautiful maneuver. And essentially what you're doing is you're making the aircraft behave as a windmill. So if these are your stabs, you're deploying each to one side or to the other. And at extreme angles of attack, this is going to cause a rotation to either side. And when you want to arrest that rotation, you provide the opposite input and the airplane is going to stop. There are some aircraft like the F-18 that do not do this well because they have built-in anti-spin design features. Then we have loaded rolls, and I am running out of time, but I still have a little bit of time, so we move on. There are like many variants, like this is like a very wide and smooth maneuver, but now we see a more aggressive one with a different aircraft pair format, much more extreme angles of attack. Here you can pretty much understand that the airflow is completely separated. So this is more like tossing a brick in the air and spinning it around. It's rather than flying a streamlined, smooth object. And this would be the most radical version, yet with another different aircraft, the Su-35S. And you can see that the plane is still flying forward, like really. It's turning around its yaw axis. It's like performing a flat spin, but it's flying forward. This is amazing. And again, this can be replicated in all its multiple forms in model aircraft. But This one is trickier than the others to pull, because there's a huge difference in inertia between a small model aircraft and a large real jet, so to speak. I mean, they are all real, but you get the point. And in order to fix this, I either need to fly faster to kind of fake the inertia through kinetic energy, or conversely, I need to fly very slow so that the airplane needs to pull really huge angles of attack to produce the lift. And last of all, and I will be finishing here, we have extreme combinations. This is a Su-57, and here it is producing a yaw maneuver. This is in slow motion, but it's barely using the rudders at all. So the aircraft is producing this motion by differential drag. It's deploying all the control surfaces on one wing and keeping them pretty much flat on the other. And this creates a difference of drag between left and right, and is what can cause the aircraft to steer even in conditions where it would otherwise be deprived of control. This is also a J-turn, or also known as the Hervás maneuver. And it is used to very quickly reverse the direction of flight. This is also a very cool one. And last, I want you to think about, before we wrap up, when fighter jets are flying at such extreme high angles of attack, you can pretty much think of them like a snow sled, you know, that thing kids go on the mountain when it has snowed and they go down the slopes. And you have like two brakes on each side, and you can pull on one, pull on the other, and then the sled will turn to one side or the other. So fighter jets, in these extreme conditions, you can deflect control surfaces in order to produce drag. And this drag will pretty much do the same effect as the brake would do on the snow sled. Last remarks, I mean, aerobatics are super amazing. I hope this sparked interest in some of you, and you will research and look further into it. I hope that you enjoy the presentation. And as I put here in the bullet points, combining theory and practice is powerful, because when you love what you are doing, you are going to learn much more than otherwise. Here are some links to some of my social media if you want to get in contact with me. And moving on to the questions and answers. So there we go. I will try and do my best to help you out, explaining everything that did not come across as good as I was planning to.
Alejandro, thank you very much for the presentation. That was really amazing. We're going to collect questions, and since people have to move in 3 minutes to another room in Partenkirchen, I'm going to ask, do we have questions from the room, Partenkirchen in the Western Grand? Let's start with that.
How many RC planes have you lost while learning these maneuvers?
I love that question. A lot. Okay, a more specific reply maybe is in order. So I have been flying for 20 years, not 18 more or less. From those 18 years, I have performed around 3,000 flights, and about half of those flights, 1,500 flights, correspond to fighter jets or airplanes that have the shape of the fighter jet. And in total, I have had like around 35 to 40 different models. Not all of them fighter jets, evidently. Fighter jets, I have mostly been playing with 4 to 6 main types of planes. And well, when I started flying, I crashed a lot, like a lot. Most of those crashes, you can usually repair the aircraft and keep flying. So despite crashing a lot, crashing in model aircraft does not always correlate to the aircraft has met the end of its lifespan. You can keep it flying as long as you can repair it, more or less. But yes, at the end of the day, it can be the thing is, you get better with time and practice. And if you do not get confidence get too much to you, because confidence will kill you, then the more you fly, the less you crash for the most part. You learn to understand when you are pushing things too bad and when you are performing maneuvers in a safe environment. Typically what you do is you will perform maneuvers. You also can practice in computer simulations before you attend in real life. There's software designed for that. And then you start practicing things like 3-4 mistakes high and slowly bring the altitude of those maneuvers down as you feel more and more comfortable with that until you will eventually crash.
Thank you. Do we have more questions from the room? We're gonna stay a bit in the meeting. Alejandro still has a few minutes, I think.
Yes.
But to the people in Partenkirchen, if there are no more questions on site, you have 10 minutes to change the rooms, but you can stick around as long as possible before the next talk walks in. We do have more questions in Slack though. How do you keep the engines from stalling at high angles of attack?
That is a really, really good question. And to honor what my aerodynamic professors did with me, I do not really have an answer for that. So I know some of the basic concepts, but I do not have the complete answers, and I would not kid you into believing that I do. Most of that usually is knowledge highly and heavily guarded by the manufacturers of such engines, but there are a few tricks that you can have in mind. So engines like to have very clean flow coming at them. So as I was talking before about the fluid, the vertical velocity profile of a fluid around an airfoil, then you also have such a vertical profile of an airflow inside a duct that is going to feed an engine. If this airflow is very uniform, then the engines usually have no problem. But of course, as the plane is traveling forward, often there is not much problem. But then as you start maneuvering, the lips of the intakes are usually pretty sharp, and they are going to cause fluid separation, which in turn generate turbulence and mess everything up. So what you do is try to work to minimize those. And a few solutions that I have seen used over the years. So the main one I've seen on Russian aircraft, for example, is that they have a grill underneath the intakes. And this is like a number of vanes, one after the other, that when the plane is flying at speed, they are closed. And then as you start reaching angles of attack, they open. They do this automatically. I think there's not even a mechanical actuator. It's just by difference of pressure, they will open on their own. So when fluid on that part of the intake inside is starting to lose energy, it will pull on the vane, open, and then you will have high pressure, high speed fluid coming from outside of the aircraft, trying to keep that in place. Another thing that is very commonly used is splitters. So if you look closely at any, and when I say any, it's pretty much any fighter aircraft design, you will see that the engines do not attach directly to the fuselage. They come very close to it, but then there is like a plate that is separating the fuselage of the aircraft from the intake itself. This is because the boundary layer that I have been talking about from the body of the aircraft is growing bigger and bigger, and it has less energy, and you do not want this to enter in the engine. So you separate the engine and allow this fluid to go to the sides.
We have a question coming, comparing predictions, numerical predictions, and experimental observations. So what are the difference between numerical predictions and experimental observations?
Okay, that's a tough one. It can depend entirely on what the problem is. And so what the definition for the problem is, sometimes you can get better predictions with one method, then you can get better predictions with the other. The real complex part usually is to predict when boundary layer is going to separate. And this, it's not just so easy to model in a computer simulation, because it takes into account very small scale phenomena, such as the rugosity of the skin of the wing, for example. And modeling this is really complex. And then even if you have modeled this in a wind tunnel, as the scale of the model grows, maybe the skin does not offer no longer the same rugosity, so this can change. But essentially what is done is CFD provides very powerful results, but you need to complement them with experimental wind tunnel testing in order to really feel that you're getting something that is representative of what you're going to have on your finished product. And another thing here, more concerning CFD and potential flow. In CFD, you are making a mesh. You're dividing volume space in small volumes. So the smaller these volumes are, essentially the more information you're going to capture. This is like taking a picture with a photo camera. And if it has a lot of megapixels, you're going to get a lot of resolution. And if you have very few megapixels, everything is going to be big pixels, and you're missing data there. Same thing happens with CFD. If you have phenomena happening on the real stuff relevant enough to shape its fluid patterns that are small enough that you are not capturing them with the size of your control volume, then you are missing entirely on that. So the results that you're obtaining may no longer predict accurately what you are going to expect. In order to solve this, it really comes down to experience, I think, and people that have dedicated their life to understanding CFD. So they kind of know from a geometry-based problem where you need to make that mesh thinner, and where you can get by with just using bigger volumes.
Thank you very much. There's one more question regarding the models that you build. How are they propelled? Are they like really turbine propelled, or do you use any other kind of propel method?
The ones that I have shown in this presentation, these are all electric. Like they are really like glorified hair dryers, so to speak. They have very small, usually 7 centimeters to 9 centimeters diameters EDFs. EDF stands for electric ducted fan. So essentially a hair dryer, which does not have a resistance to heat up air, but it's only moving air around. And you power this with lithium polymer batteries. But the thing is, you're trying to move machines, at least the ones in my videos, that are ranging from 3 to 6 kilos with very, very small propellers that they are, because efficiency goes with the span on a wing, and a propeller is just like a wing that is rotating. So from being such small propellers, they are really, really not efficient. And to make things worse, since these airplanes attempt to be scale replicas, you need to move the air through a long, long duct, and this will cause further decreases in pressure. So it's really, really inefficient. And these are planes that are consuming, when I'm full throttle, it's like 3 kilowatts of power, depending on the setup. And you drain the batteries in around 3 minutes. So
I imagine
you don't get to fly for long with this, but they are cheap and affordable. Then you also have actually kerosene engine powered fighter jets. And actually, at the time being, I'm trying to get into this world. I'm making the steps. As everything in this hobby, one tries not to go to lesson 10 before first having made 1, 2, 3, 4, 5, etc. But I'm getting close to that, and I hope I will be flying kerosene-powered turbine aircraft in the future. And one other thing, these kerosene engines, which is not what I'm using yet, but they exist, and it's a big thing. And then you are often flying models that are no longer 4 kilos, but maybe 20, 25 kilos, and even bigger and heavier models, although right now there's some problem with regulations in the European Union as to larger aircraft, but I guess we will eventually sort that out. These engines are not exactly, they do not work exactly like the full-scale jets. Typically, you have on turbofans, either for commercial aircraft or fighter aircraft, you have axial flow. That is, the flow comes straight at you and pretty much follows a straight path inside the engine. Instead, turbines for model aircraft use axial compressors. That is, the airflow comes straight, and then you compress it to the sides. So it's more similar to how helicopter engines work in that fashion.
Thank you very much. Alejandro, thank you very much for answering all these questions. Thank you for being with us. The time that we have is up. I believe you will be around on Slack for a bit longer. If there are further questions, you can contact Alejandro directly or via one of the methods he provided on Instagram, Twitter, and so on. Thank you very much again, and enjoy your day.
Thank you for providing me this opportunity.